Okay, in this problem, we're given a piecewise defined function. We have three pieces here, and we're asked to find the limit as x approaches 0 of that function, and to give a graphical interpretation. Okay, so again, initially you might ask yourself, well, can I take advantage of continuity? Is f of x continuous at x equals 0? Because if it is, I could just plug in 0 into my function. Whatever answer I get out, that's going to be the value of the limit. That's what we mean by continuity, that the limit and the functional value both exist and agree. Okay. Unfortunately, if we're interested in what's happening as x approaches 0, it's not immediately clear what f is doing. We have different behaviors at 0, left of 0, and to the right of 0 in this graph, or in this function. So with that in mind, let's go ahead and graph this guy, just to get a better feel for what's going on. Okay. To the left of 0, that's our first piece. Okay, x is less than 0. F of x is identical to the function x plus 2. Okay, so if I were to graph y equals x plus 2, of course that's a linear graph. It's a slope 1, y-intercept of 2. Come up here, 1, 2, and then draw that in. Notice I've only drawn it in for these x values when x is less than 0. And in fact, because I don't have equality here, I need to be very deliberate and make sure I've indicated that's a hole right there on the y-axis. Okay. This next piece, I know that my function will give me a height of 0 when x equals 0. Well, that's only a single x value, so it's going to correspond to a single point, namely at 0, 0. Okay, so I'll fill in a hole there. And then when x is bigger than 0, when it's greater than 0, or when I'm talking about to the right of the y-axis, it looks like my function is identical to the constant function whose graph is given by y equals 2. So that would just be a horizontal line. Okay, again, because I don't have equality here, I need to make sure I indicate that with an open circle. Okay, so the question is, if I'm to evaluate the limit as x approaches 0 of f of x, I need to find the height that I can get arbitrarily close to as long as I keep my x values sufficiently close to 0. Okay, in other words, what's the behavior of this function as I'm getting closer and closer to 0? Well, if I approach from the left, as my x values get closer and closer to 0, look what's happening to my heights. They're rising up to a height of 2. And on the right, as my x values get closer and closer to 0, what's happening to the height of my function? Well, it's staying 2 the entire time. So it's also, in a certain sense, approaching a height of 2. Okay? So it should be clear from the graph that the limit as x approaches 0 of f of x is indeed 2. And sure enough, that is our answer. But it's important to realize that you can evaluate this limit without ever graphing this piecewise defined function. Okay? So how do we do that? Well, let's write this function down again. So f of x equals x plus 2, that's one piece, when x is less than 0. It's 0 when x equals 0, and it's 2 when x is greater than 0. Okay, we've got three pieces here. Just as visually, I looked at this function and said, well, what's this guy doing as I come in from the left? As my x values get closer and closer to 0, but just from the left, what's happening to the heights of my function? And as x approaches 0 from the right, what's happening to the heights of my function? I can ask those same two questions algebraically. Okay? I can limit my attention to only x values approaching 0 from the left. Okay, if I write the following. So limit as x approaches 0, and then to indicate that I just want to look at the x values that are left of 0, I'm going to put a little minus sign right here. Okay, that restricts it to only coming in from the left-hand side of f of x here. What does that equal? And in a like manner, what happens in the limit as my x values approach 0, coming in only from the right? So here I'll say x approaches 0, and then just like up here, I'll indicate only from the right with a little plus as a superscript on the 0. Again, we're taking the limit of f of x. Okay, I want to answer those two questions. I want to find out the value of those two one-sided limits. That's what these guys are called. When you put the little minus there or the plus there, you're talking about a limit coming in from just one side. This is the left-sided limit, and this is the right-sided limit. Okay, and again, graphically, we said this rose to a limiting height of 2. This stayed 2 the entire time, so it also had a limiting height of 2. I want to somehow get 2 out of this. But look, if x is approaching 0 from the left, in other words, the only x values I'm ever concerned with are left of 0, and hence less than 0, okay, then this piece right here determines what f of x is. Okay, this is the same as the limit as x approaches 0 from the left of x plus 2. Okay, now we know what happens when we look at the limit as x approaches 0, whether you're talking about the left or right or either direction, the limit of this x plus 2. This is a linear expression. This is a polynomial expression. This is a continuous function. Continuous functions are, it's real easy to take limits of continuous functions at points where they're continuous. You just plug in the value of x. That's 0 plus 2 or 2. Down here in the same manner, if we know the x's we're looking at are to the right of 0, what is f of x to the right of 0? It's completely determined by this piece. It is then always 2. So this is the same as a limit as x approaches 0 from the right of just 2. Okay? Again, just like x plus 2 before it. This is a very simple function, and more to the point, it is a continuous function. If I want to know what happens when x gets close to 0, whether it be from the right or the left or any direction, I can just plug in x equals 0. And of course there's no x to plug in here. Since it's just a constant, we just get 2. Okay? So evaluating these two things algebraically answers the question, what's happening to my function's graph and the heights of that function as I approach 0 from the left and as I approach 0 from the right. There from the left, there from the right. And in both cases, it looks like we're approaching a height of 2. Because these two things agreed, okay, because I got the same value out, then I can say limit as x approaches 0 of f of x equals 2 more generally. All right, which is the same thing I got up here, except for I really just did this algebraically. I didn't need to know what the graph looked like. I appealed to continuity here and here to evaluate those two limits. Okay, so that's the value of the limit. Graphical interpretation, again, looking at the graph, it's very easy to tell. It's just a hole, and I can specify exactly where that hole occurs. Not only does it occur when or at x equals 0, but I know the y-coordinate. It's too high. So let's say this is a hole at 0, 2. Okay, that's the graphical interpretation. Again, you don't have to graph it to figure that out. We have a value for the limit. Okay? If the original function's value at 0 either fails to exist or disagrees with this, that's when we get a hole. Okay? So note f of 0, right, this value right here, If we go back and plug it in, well, let's see which piece pertains. It's this one. We get an output of 0 because this and this disagreed. That's what tells us we have a hole. Okay? Also, if this failed to exist, we would have a hole. Okay? That's it. That's the value of the limit. That is the graphical interpretation. We're done.